Hi, welcome to a very unique video where for the first time we are going to go into the fundamentals of our AI journey. We all are students of AI, isn't it? Now in this video, we are going to go to the basic fundamental block which each of us should know about. So it's a very important video. Please watch and understand this completely from start to finish. Welcome to Techie Talks AI. I'm Sri from Shogini. On this channel, we bring you hands-on demonstrations and insights into the latest tools and trends to help you get started with ease. Don't forget to subscribe and be a part of our journey into the future of technology. We all know that machine can learn and how a neural network works, but the fundamental one neuron or one perceptron, how it learns is what we are going to look at. I have created a web application to highlight this aspect. Okay, so we'll go through the demo of that web application. That will make this very, very clear. Okay, so setting the stage, why Perceptron? Why deep neural networks? Perceptron solves AND OR gate. So these are digital gates. So let's look at this picture. So this is a logic gate which we all would have studied. And this can be AND, OR, and maybe XOR, etc., NAND and things like that. Okay, so if it is AND, we would draw like this. If it is NAND, we put a NOT operation like this. So this was a simple digital logic gate. So if it is an AND gate, then when this is 1, this input is 1, then you get a 1. All of the conditions, it will be 0. Clear? So if you draw a truth table, 0, 0 will result in 0, 0, 1 will result in 0, 1, 0 will result in 0, and 1, 1 will result in 1. So this is one input, and this is the other input, and here is the output. Okay, so that is the truth table of an AND gate. Now, what is the connection with Perceptron? Perceptron is some kind of a mechanism which can process inputs and produce an output, just like an AND gate. So here what happens is this input and this input can be computed by the perceptron in such a way that it can produce an output. Now, by adjusting the weights on this and weights on this, these weights are a multiplication factor. By adjusting the weights on these inputs, this can control the influence these inputs have on the output. So essentially, we multiply the weights with the input value and add it, and then add a bias, and then we have an activation function which will produce 0 or 1. Got it? So that is a perceptron, and this is not something new. The idea is similar to neuron, not exactly, but similar to how our neurons work. So now coming to our presentation, setting the stage, why perceptron, why deep networks? So let's look at this slide. A perceptron is one simple artificial neuron. This is somewhat similar to neuron, can easily learn basic logic gates. Got it? AND gate. So in case of AND gate, we saw output 1 only when both inputs are 1. And OR gate, output 1 if any one input is 1. It does this by learning straight line boundaries between inputs and outputs. However, a single perceptron cannot solve the XOR problem because the XOR has a curved boundary. So let's see what that is. Let's try to plot. Okay, so this is X and Y axis, and here, so this is input 1, and here we have input 2, and this is 0, this is 1. Okay, so this is a 1. So in case of AND gate, both inputs are 0, output is going to be 0. And if one input is 1 and other input is 0, there also output is going to be 0. Okay, and Here also the output is going to be 0. This is clear. If both inputs are 1, the output will be 1. So here it is easy to draw a boundary. So if the learning algorithm, by adjusting weights, if it can figure out this line, it can classify the output and produce proper results. So learning is possible with a single perceptron. We will see that. I have made a demo web application to highlight this. And OR gate also is similar. This will be 1, this will be 1, so the line will move to here. But when it comes to XOR, this will be 1, any input becoming 1 will be 1, and both input becoming 1, XOR will be 0. Clear? So you need to have 2 decision boundaries to generate an XOR. For this, you need a multi-layer perceptron. Clear? So I will demonstrate how single perceptron cannot handle XOR in our learning phase when we see the demo. Okay. So because XOR needs a curved or multi-part boundary, single perceptron cannot simulate it. Okay. So this shows a limit. Simple models solve simple problems. To solve complex problems like XOR, we need multi-layer perceptron or MLP, and which is a deep neural network, DNN. Okay. So similarly, traditional statistical machine learning models like logistic regression, support vector machine, SVM, work for simple patterns but fail in complex high-dimensional data. Neural network allow us to break the complex problems into simple intermediate steps handled by these layers, making them incredibly powerful. So we don't need very sophisticated statistical models before we begin the learning. Okay, so now it is demo time. So let's run the Perceptron Playground app which I have created. You can train the tiny brain, single perceptron, and see how it learns, makes decisions. So here is the Perceptron Playground which I have created. Now here we have an AND gate, and for AND gate, this is the training data set that we will use. Here we have input 1, input 2, then we have the output. So there are 4 different combinations, and only for one combination output is 1. See this? So I have created the picture of the perceptron here. This is the perceptron, and it has got input 1, input 2, and then some parameters. In a large language model, we talk of parameters. They are the weights. See here, they are the weights and the bias. So what happens is the input value gets multiplied by the corresponding weight, and they are all added together, and then finally the bias gets added to that total. And then an activation function will decide the condition needed for the output to be 1 or 0. So the learning process is adjusting these weights and biases. So here at the start of the operation, these weights and biases are randomly set. So here we can see the weights and bias, they are randomly set. So just like a newborn baby. So now here, if you see, I'll make this input 1, the output is always staying true, which is not the correct condition for an AND gate, isn't it? So what I'm going to do is I'm going to click on train fully. Each training loop can be called an epoch. 4, 5, it is trying out different weights and biases. See the weights and biases changing, a number of mistakes reducing, and finally it got 0 mistake. And now if you check the input, make this 1, output is 0, make this also 1, see output becomes 1. So this works perfectly like an AND gate. And here is the calculation that is given, weights and biases, and then the picture also is updated. So this is a very nice playground using which we can teach people who are learning, coming into this field of machine learning and neural networks and deep learning, LLM, etc. So this is an excellent way of making the point clear how a single perceptron learns. So now let's do the same thing for the OR gate. Let's train fully. I have also given a train step button which will train one epoch at a time. So OR gate training is over. Any input becoming 1, output is 1, and both inputs 1 also, output is 1. Now comes the XOR gate. Shall we train this fully? Let's see what happens. Epoch 1, 2 errors, 2 errors, epoch 6, 9, 3 errors, till we put a limit to number of epochs. This will go on in a loop without converging. That is, how much ever you adjust the weights and bias of a single perceptron, this will not converge into a solution which will result in this condition, XOR condition. Clear? So let's stop it. Let's reload. And now, just for understanding, I have put some exercise decision. Just a fun thing to make it more relatable to real life scenario. So here I have a training data set. I will show you the code, how I have created this input data set. Click on train fully. So here we have mother, father, sister, brother, teacher, a student agreeing to exercise. There are more number of inputs, so it is taking more number of epochs to arrive at the needed output. Okay? Mistakes made 0. So this is the condition. So if mother tells, the child doesn't listen. If father tells, child listens. Mother and sister tells, it listens. If teacher tells, it listens. Because mother is very close to the child, normally we take the instructions from the mother for granted. Okay, clear? This is the picture of the exercise decision-making perceptron. Mother, father, sister, brother, teacher, and the bias value. Okay? Now coming to another example, rain prediction. Cloudy, monsoon, high humidity, windy, cool temperature, and target output. Whether will it rain or not rain. So this is the perceptron. So let's go over the code. So here I have defined the problems, AND gate, inputs. So inputs and the output. XOR gate, exercise, decision, each input, mother, father, sister, brother, teacher, and then the output. Rain prediction. So like this we can create our training data set for the single perceptron. Anytime we change the problem, we are setting the weights randomly and setting the bias also randomly. So here we have set the limit of this epoch to 50. So this is an important aspect because this will decide how much energy, how much money we need to spend in the training. So when you notice that the errors are reasonably low, then you can stop the training, and large language model will take weeks and months for completion of this training. This is where we are altering the bias and weights from the learning rate. Learning rate we multiply with the error and with the input. So learning rate, so here we are setting the learning rate to 0.1. So these parameters we will need to adjust for best learning experience. Okay, so all the code that I am showing here is available for you to also experiment. Let's get back to our slides to complete the video. So let's look at the origins of this perceptron. In 1958, a scientist named Frank Rosenblatt invented the perceptron. So first machine designed to recognize pattern. It was a mechanical device. 1958. Okay, perceptron is just inputs, weights, bias, and activation. We saw that in the demo. It was one artificial neuron inspired by human brain. So how Perceptron works, it multiplies the input by weights, add a bias to the total, then apply an activation. In our case, it's a step activation function, and output 0 or 1. And like we saw, a limitation of a single node perceptron cannot handle XOR problem. And where the single perceptron fails, need multiple regions to make the decision. Multi-layer perceptron MLP to the rescue. Hidden layers split the problem. So each layer can address different patterns. Combine symbol regions smartly, and XOR is now solved. And then the rise of deep neural network. So scientists stacked more and more layers made of perceptron, and deep neural network could now recognize handwritten digits, understand speech, classify images, whatnot. We saw the revolution. Neural networks are growing smarter every day. Now, special customized neural networks started. So CNN, see and understand images. RNN, read sequence of text. LSTM, remember important things for longer periods. So LSTM is a more sophisticated version of RNN, recurrent neural network, which will not easily forget the context. Then Transformer, the giant leap. We saw the revolution, ChatGPT revolution. 2017, the paper Attention is All You Need showed that focusing on important parts of the input made the learning much faster and better. No more slow training, and now AI could learn massive amount of data more efficiently. From transformers to LLM, GPT, Claude, Gemini, Llama, DeepSeek, and understand, generate, and reason, and revolution in AI capabilities. Okay, so we are living in the middle of this revolution. What is inside an LLM? Inside an LLM, millions of small artificial neurons organized smartly using attention and deep learning, trained on huge text datasets. At their core, they are still tiny perceptrons, multiplied, stacked, and organized into something unimaginably massive. Final reflection: from one simple perceptron in 1958, layer by layer we built AI systems that can think, write, and reason. One small idea built smartly is changing the world. So thank you for joining this amazing journey. The smallest unit of a large language model should be very clear to all of us now. Thank you. See you in the next video. Please remember to like, share, and subscribe, and give your valuable comments. Bye-bye.